Welcome to this IB Maths Intense session, second session on counting principles, this time looking at the idea of permutations. And we'll be focusing in this session on the nice, simple, straightforward permutations work. In a following video, I'll look at the more tricky, testy type of questions that we might be asked where there are restrictions or special cases. But this should give us a nice introduction to the idea of permutations. Syllabus link shows that this is a higher level only concept. So if you're a standard level student, love to have your company, but it's not essential that you listen to this video. In the context of what we were doing before, permutations work follows on nicely from the work on factorial notation in the earlier video and will lead into questions at a later stage in probability. It's a higher level only concept. So what is a permutation? Well, a permutation is a unique arrangement of items chosen from a set. So in the example here on the screen, you'll see I've got three cards, A, B and C. And I'm interested in how many different ways, unique ways, could I arrange those three cards if I laid them out in front of me. Now I could just list the possibilities. I could put A, B, C down, I could put A, C, B, I could put B, A, C, I could put B, C, A, I could put C, A, B and C, B, A. And that's, I think, all of the ways that I can arrange them. It is, and we'll see that there are 6. Now you really don't want, as a higher level mathematician, to be having to list all the possibilities, all of the permutations, unique arrangements when you're asked a question. We want to be able to do this numerically. So another way of looking at that is to say, if I'm going to arrange all three cards, how many ways could I select the first card? Well, there are 3 ways of selecting the first card. And then the second card, there's only 2 cards left to choose from. So that's 2. And the third card, there's just 1 left on its own at the end. So 3 times 2 times 1 gives me my 6 unique arrangements. And that's a rather easier way than having to list all of the possible unique arrangements. Now hopefully you can see 3 times 2 times 1, if you were watching the earlier video, is 3 factorial. And if we try and generalize this now to a larger number or to n objects, in fact any number, we'll see that there's a nice easy result. So this time I've got 5 cards to choose from and I'm going to uniquely arrange them. I don't want to list the possibilities, it would take me all day. So I can think of it as there are 5 ways to choose the first card, 4 to choose the second card, 3 the third, 2 the fourth and just 1 left at the end to give me a total of 120 unique arrangements of those 5 cards in a row. Now that, as you can see, is just 5 factorial, 5 times 4 times 3 times 2 times 1. So if I have n objects and I want to arrange them all in a row, how many ways can I do that uniquely? Well, a nice simple result. It's just n factorial. So if you end up with a question like this, how many ways could all 26 letters of the alphabet be arranged if I laid them out in front of me? How many unique ways? Well, it would just be a task for your calculator. 26 factorial, which everybody knows off the top of their head, is 4.032914611 times 10 to the power of 26. That's an amazingly large number, a huge number of arrangements of the 26 letters of the alphabet. But that's not it, unfortunately. It does get a little bit more complicated. Sometimes I don't want to arrange all of the cards. I want to select a number of cards from the set and uniquely arrange them. So here I've got 5 cards, A, B, C, D and E, and this time I want to know how many ways can I uniquely arrange 3 cards chosen from that set of 5. So using the same kind of logic as before, far better than listing them, I could say how many ways, there are my 3 cards that I'm going to choose. I could choose the first card from 5. There are 5 ways that I could choose it. The second card, there's only 4 left to choose from now, so it would be 5 times 4. And the third card, there would only be 3 cards left to choose from. So 5 times 4 times 3 gives me 60 unique arrangements of 3 cards chosen from 5. Now what we want to be able to do is to generalize this to create a formula so that we don't have to keep multiplying a large set of numbers together. Imagine we had 50 items and we're choosing 45. I don't want to do 50 times 49 times 48, etc, etc, etc. So thinking about what we did before with factorial notation, we can look at this result and see that this could be written as 5 times 4 times 3 times 2 times 1 divided by 2 times 1. Then my 2 times 1 would cancel down. In other words, it can be rewritten as 5 factorial over 2 factorial, because we know from before 5 factorial is 5 times 4 times 3 times 2 factorial divided by 2 factorial. Now, what I'm going to do now is try and generalize this. So on top, here is the number of items that I'm choosing from, n factorial. And on the bottom, 2 factorial is the difference between the number of items that I've chosen, 3, and the total. So in other words, it's n, my total, minus r, the number of ways, the number of items that I'm selecting and arranging. So my formula generalizes to n factorial over n minus r factorial. And this is the formula for NPR, where n is the number of items and r is the number that we are going to arrange, chosen from that set of items. And P obviously stands for permutations. So NPR, how many ways can I arrange r items from a set of n? And that generalizes to the formula n factorial over n minus r factorial. And sure enough, there it is on our formula sheet. Under AHL 1.10 permutations, NPR is n factorial over n minus r factorial. So let's have a look at a few simple, straightforward questions that use this logic. So just like the ones at the beginning, how many ways could the letters of the word IB Maths be uniquely arranged? Well, there's 7 unique letters in IB Maths, so this would just be 7 factorial, because I'm using all of the letters. And 7 factorial gives me 5,040 unique arrangements of the letters. If I had the same set of 7, but this time I'm only going to arrange 4 letters selected from the word, well then I could use, using my permutations notation, 7p4. I'm going to arrange 4 from 7. And I could put that into the calculator to get my result, or I could write that down using factorial notation. That is 7 factorial over 7 minus 4 is 3 on the bottom, 7 factorial over 3 factorial, and that gives me 840 arrangements of the 4 letters selected from 7. 840. How many ways can 5 letters selected from the alphabet be arranged? Big question to finish. Well, this time 26 letters of the alphabet, and I'm choosing 5. 26p5, which could be written using factorial notation as 26 factorial over 21 factorial. And my calculator will show me it's another large result. They're going to be 7,893,600 unique arrangements of 5 letters selected from 26. Quite straightforward. Hope you found that useful. We'll look at the more complicated questions with restrictions and special circumstances in a following video. But for now, hope you found that useful. Thank you for watching. Don't forget to like the video, subscribe to my YouTube channel, IB Maths Intense. Tell your friends that I'm here. And if you've got any questions or special requests for particular sessions, email me at ibmathsintense@gmail.com. So, enjoy yourselves, enjoy your maths, and take care.